Good afternoon, everybody. Welcome to our digital event. My name is Marwan Shida. I'm the head of digital transformation and innovation in the SESAR joint undertaking, and I will be your host for today. Artificial intelligence. So many questions around artificial intelligence. What is it exactly? Is it a real thing or just a hype? We are aviation, we are safety critical. So is it really safe? Are we ready? And how do we compare to the rest of the world? If you are looking for answers, the Fly AI report and the webinar series are really designed just for that. For example, the first webinar covered the importance of partnership, so how we should work together to progress on the AI front. And other webinars coming up will talk about important topics such as certification or data. And here we are today to talk about research and innovation. how advanced is research and innovation in AI for aviation? This is the question of the afternoon. And to answer this question, join me in welcoming our panelists and speakers today. From Brussels, we have with us Mr. Florian Guillermet, the Executive Director of the SESAR joint undertaking. From Singapore, 9 p.m. local time, we have with us Dr. Samir Alam, the Associate Professor at the NTU University and Deputy Director of the ATM Research Institute. Florian and Samir will try to give us the helicopter view and the big picture before we dive into the key European developments in the area of research and innovation in AI for aviation. And there, joining us from France, Georges Papageorgiou, Technical Director of Advanced Technologies of Honeywell Aerospace. Coming up from Sweden, Robin Hughes will be with us today, former Head of Engineering of LFV, the Swedish air navigation service provider, and Director of the Autonomous System at RISE Sweden. Joining us from Spain, Ricardo Sanz Amand, Director of Security and Defense Programs at GMV, representing the European Defense Agency, and Dr. Hartmut Emke, Scientific researcher at the German Research Center, DLR. As you can see, we had put together more than a century of ATM and aviation expertise to try to answer your questions. And hopefully, at the end of this webinar, you will get a much better feeling about where do we stand in terms of research and innovation. You see, we have a very interesting program ahead, but before we start, I would like to give you some housekeeping instructions. This event is broadcasted at YouTube and LinkedIn. And for the lucky ones joining with Zoom, you will have 3 possibilities to interact with the crew. If you're experiencing any technical issues, please use the chat button. Then you can have a chat with our crew here about any audio or video issues. If you want to ask the panelists any question, please use the Q&A option. Remember to have a look at the other questions and vote for the ones that you like. That will help me moderate the panel later on. We have a Q&A session, and it will help me look at the most popular questions. And the last, but not least function that I like is the poll. Some of our speakers would like to put you to work and ask you some questions so that we could make the session as interactive as possible. Without further ado, I would like to introduce our first speaker, Florian Guillermet. Florian, you are the director of the SESAR joint undertaking. Your organization is in charge of modernizing the ATM in Europe. So why AI is such a big deal for aviation in Europe? Maybe Florian is a bit muted. Florian, sorry, we don't hear you.
Can you hear me now?
Excellent.
Good, great, thanks. Good afternoon, everyone, and thank you, Marwan, for this introduction. So indeed, I'm not an AI expert. I will simply try to kind of set the background of why AI matters, in particular in the context of a program like SESAR. And I'd like, first of all, to... it's okay, yes. Okay, sorry, I had some interruption here. So why it matters like in a program like SESAR, and first of all, I wanted to thank the Fly AI high-level working group for this series of webinar. I think we all have to learn together about what AI can bring in the context of a safety-critical system like aviation, and in particular air traffic management. So just to try to set the scene, as I was saying, I mean, this is a bit how I see the current aviation system. Don't get me wrong, it seems to be a bit weird to make this analogy with a tree and a pot, especially in the context where we have all those difficulties about the COVID situation and the aviation system somehow that is kind of shrinked for the time being. But my view over the last decade, let's say, of development of aviation is that to a large extent, aviation is becoming bigger than its infrastructure pot, to mix the analogy with the tree and the pot. To a large extent, we had a growing system in terms of numbers of vehicles, but as well in terms of a higher degree of complexity, as well as in terms of the number of services that could be provided from the sky, including the traditional air transport, commercial air transport for passengers, for freight, but as well now a number of newcomers that are knocking at the doors of our skies to provide all sorts of kind of new services. And here I'm talking about the drones, but as well the high altitude airspace operations and so on and so forth. So to a large extent, the aviation ecosystem and the aviation operation has gone quicker than the infrastructure, than the way we manage its operations. And in my view, this is typically where AI kicks in to provide potentially a number of solutions to these difficulties that we see facing, and that materialize very heavily in the context of the 2018, 2019 traffic growth that we had in Europe, with a big congestion of the airspace, delays everywhere for the airspace users, but as well the pressures that we put on the new entrants that are again trying to access the system, that have difficulties to access our skies because we have a lot of restrictions for them. So if I look at how we see the evolution of the future system, and please keep in mind that this is just an introduction to pitch how AI could fit into this picture, what we do see is that the vision of the future skies has changed quite a lot over the last few years, moving from a rather rigid structure where basically we move the traffic where the capacity of the airspace is, to a structure which is much more matching this view of a digital European sky vision, where we provide the air traffic services where the demand is, where we provide the services where actually there is a need and when there is a need. And for that, obviously, we need to change the way we organize the airspace, and this has been the purpose of a study we published about 2 years ago, the so-called airspace architecture study, which highlights a number of new changes that are coming in the way we're going to handle our skies. First of all, more connectivity between the vehicle and the infrastructure, a higher degree of automation. Here, I'm becoming very careful in the sense that the idea is not to have a fully automated system. It's to acknowledge the fact that automation can support the work of the controller and of the pilots to provide not only safety, but a higher degree of flexibility, of efficiency into the system. The use as well of a number of techniques like virtualization. And finally, the fact that we rely more and more on a number of data that have to be provided through services. So the fact that we move progressively from, I would say, an understanding that this system is about a physical infrastructure, that we are dealing with physical assets to digital assets, to a more digital infrastructure based on services. This is absolutely fundamental, I believe, in particular in relation to the challenge that we all face in aviation about sustainability, the fact that progressively we need to make sure that the skies are coping with the best trajectory possible for the aircraft and for all types of vehicles that are going to access into the airspace, and that we don't basically constrain the trajectory because of the constraints we face in the infrastructure, but that we put the system the other way around, that we build a system that can accommodate, that can make sure that the aircraft, the vehicles can actually fly their optimized trajectory in terms of sustainability. So my expectation of the discussion today is really to better understand how AI can play a role in this new environment, can bring this ecosystem to a new different level, and to as well kind of give you a flavor of what we do witness in our project, which is that more and more higher degree of automation as well as new services can be supported by AI application. So I'm really looking forward to the discussion that we're going to have with you guys as experts later on, and I want to thank you for giving me this opportunity just to give you this kind of scene setting. Thank you, Marwan. Over to you.
Thank you very much, Florian. Thank you. It's our turn to thank you as well, because we need a sense of purpose about why we're doing this technology. It's not the technology for the sake of technology. It's really technology to, as you said, to bring a new pot, a bigger pot to the aviation tree. Now, to give a bit of perspective, I would like to hear from Samir. Samir, you are involved in many research activities worldwide. And I would like to hear from you about how you see the progress of AI in aviation as a sector.
Hi, thank you, Marwan. Hi, Florian, and hello, respected speakers. And good morning, good afternoon, good evening, wherever you are. So let's hear something from a crazy scientist perspective on what AI can do for air traffic management. And in today's presentation, I will be talking about this vision about hybrid AI human air traffic management systems. So my question to you is, what makes this possible? Whether it's the recommender system from Amazon or the Echo, which is the home virtual assistant, or the spam that you see in the Google mails, or
Samir,
the Google driverless car.
Sorry to interrupt you. Can you put it like slideshow? Because I think so that everybody enjoys the pictures, the nice pictures that you have there.
Is the slideshow not up?
Yeah, it's up now.
Okay, so I think it's a bit slow. So these technology or these revolution that you see recently are made possible, as you know, because of the artificial intelligence and a sub-specialized branch of machine learning. And these topics are appearing, you know, in all countless articles, even outside the technology-minded publication. And when we see these things happening, we are promised a future of intelligent chatbots, self-driving cars, and virtual assistant. A future sometimes painted in a grim light, and other times as utopian, actually, where human jobs will be scarce and most economic activities will be handled by robots or AI agents. And as Marwan rightly said, that air transportation is a safety conservative domain. And for AI to play a role in the evolution of the future ATM system, it is very important that we understand and recognize the signal in the noise, so that we can see what are the world-changing developments here from the overhyped press releases. So in my presentation, I will tackle these questions. What AI and machine learning has achieved in aviation, how significant it is, and where we are heading next. And should we believe the hype? So as we all know that we have a plan. We are preparing the air transportation for the industry 4.0. We can see in the recent publication, there is an evolving roadmap and strategies from the major players in terms of significant reports and publication. If you go through these reports, you will observe that there is a common theme in them. There is a specific stress on the research and development on the human-machine collaboration. As Florian has rightly mentioned, there is a need of coming up with solutions which are both human and machine co-developed and co-teamed. Even the research community where I come from has started taking notice of it. As you can see, we have major conferences in ATM R&D seminars, SESAR Innovation Days, ICRAT. They all have specific sessions, special sessions focused on machine learning and AI. There is a special conference even in Singapore that happened in 2020 that I organized, focusing on AI and data analytics for air transportation. If you see this chart from Google Scholar with the keyword air traffic management plus AI, you can see the number of publications are growing exponentially now. In 2020, over 1,000 research papers were published where AI was applied to air traffic management. So there is a growing pickup of machine learning techniques in the ATM community, and which is very significant. As you see, it's almost doubled in the last 5 years. So let me go through quickly why machine learning approach in this sense. So as you know, in the traditional way, we have a conflict scenario. Let's see the example of conflict detection and resolution, the classical problem. We have a conflict scenario and we have separation standards. We feed this data and the rule into the classical CDNR model, right? And based on the separation standards, the machine or the algorithm can tell whether there's a conflict or not. If there's a conflict, controller will take action to level off or whatever. So this is the classical technique. As you can see, the search space here in this case will explode exponentially. The choices and the scenarios will be such that it will be impossible to encode. So machine learning algorithms are very powerful where it is very difficult to encode the actions. So let's see how a machine learning algorithm work on this problem. In machine learning, yes, the conflict scenario is the same, but instead of the separation standards or the rules, we input the controller actions. So how controller has solved them is what is inputted to the machine learning model. And this paradigm helps us to learn the rules. So instead of hard coding the rules, getting smart programmers and hard coding the rules, let the machine discover the rule by itself. And once the machine is exposed to the unseen conflict scenario, it's expected that it shows these various actions to the controller. Then controller feedback about these conflict resolution strategies selected by the machine learning, and the machine can update his belief. So this is the co-teaming or the hybrid human paradigm that we are working on at the moment. This paradigm actually combines the expert judgment with the relevant data. This Venn diagram illustrates the philosophy of combining the neurophysiological information, the air traffic control actions, and the data coming from ASM, GCS, ADS-B, radar, etc. And then to use this myriad data and learn the patterns from them and use these patterns to predict the actions. And again, update the patterns based on human actions. So now I will show some of the research that we are doing at Air Traffic Management Research Institute in Singapore. On this screen, you can see the opportunities machine learning provides for airport airside optimization. So on the top left-hand corner, there's a non-metering traffic on the air side, aircraft going from the apron to the runway. The blue are the departures, the red are the departures, and the blue are the arrivals. And they can be congestion, they can be deadlocks. But in the lower left-hand side, we can see intelligent metering happening. Here, the machine is able to learn the arrival and the departure patterns and is able to do the taxi routing with the predicted velocity. And this leads to a spatio-temporal taxi routing, which when combined with the predicted information can also do some hotspots prediction, even telling the controller that these are the areas of the taxiway which are predicted to be hotspot. So this, all these slides have research publications at the bottom where these research are peer-reviewed and published. The next I will show you is a fantastic opportunity which machine learning or specifically deep learning offers for runway optimization. So in this case, we are looking for learning the free departures. Can a machine learning algorithm learn the arrival stream, learn the wake vortex, can learn the ROT, and able to push the departures. So here you can see on the right-hand side is the TMA airspace of Zurich Airport. The data aircraft is coming in here. On the left-hand side is the aircraft incoming and landing. The green one aircraft are waiting for departure. And as you can see, there's a confidence bar which shows the agent confidence, whether it's ready to push a departure or not. So this is very important as an explainable AI, where the AI agent is advising the tower controller whether what's my confidence level to recommend this push to recommend this push to go, and controller then can collaborate with the AI agent to insert the free departures in the stream of arrivals. This is the other research. Here we are showing how we can use the AI to train the AI agent using human in the loop. So on the top left-hand corner, we can see the simulation environment, and the air traffic controllers interact with this environment to give various conflict resolution. The lower corner, which I've just put the animation on, is the space-based ADS-B data. From this information, various the various conflict resolution strategies can be learned. And on the top right-hand corner is an abstract environment which abstractize this information, and controller interacts with this environment, and AI agent is learning while controller is interacting with these three environments. Once all this training is completed, then the AI agent is exposed to unseen scenarios. and it is able to recommend conflict resolutions, which is very similar to the controller own strategy. So remember, I showed you the Alexa, I showed you the spam filter. What was unique about it? It is yours, it is personalized. It is learning from you itself. So here in this case as well, the conflict resolution strategies are learned from the controller. Therefore, there is less chances of controller rejecting them. This research is about digital control towers. As we know, there is a significant research happening about remote towers and digital towers. So on the top left-hand corner shows the power of deep learning to track the various entities at the airports, whether the bridge or aircraft, fuel truck, and how much time it is going to take. It's able to predict the aircraft pushback time using the deep learning techniques. This research was recently published in the SESAR Innovation Days a few months ago by my research group. On the lower side, you can see the deep learning just by using a single camera can track the aircraft and in real time show the distance between them for any anomaly detection. On the top side is the digital simulation environment. Not only the aircraft, but which segment they are, how far they are, what's their speed is all visible to the digital tower controller. In the lower side, I'm showing a 3D printed airport. A 3D printed airport with the HoloLens interface. So this is Microsoft HoloLens with that inbuilt tracker, eye tracker, as well as Kinect sensors. So a virtual controller can interact in this environment while having the AR and VR interactions. So as I move forward, these are the open research questions that we see in the community. There is a lack of trust of air traffic controller in the AI and machine learning system. And we have to build towards the trusted, autonomous, and human hybrid ATM system. There is an integration issue that we are facing of the AI system with the ATM system, certification, and then there's a safety verification and validation challenges. Also, there has to be a need for post-accident audit mechanism. So these are the open challenges which research community at the moment is tackling head on. So this is my brief overview of the research that we are doing here in Singapore at the Air Traffic Management Research Institute and at the Saab NTU Joint Research Lab on Digital Tower. If you have any questions and feedback, let me know, and Samir Alam at ntu.edu.sg. Thank you so much.
Thank you, Samir. Thank you very much. I think we are human learned a lot from your presentation, and honestly, I always surprised how much you are knowledgeable about what's going on in the world and what's going on in Europe. And I'm pretty much like this concept of a partner that is there. Let's say you go there, you connect, and then you have your digital assistant that knows your behavior, knows what you like and what you dislike.
Thank you.
Now we are going to enter a deeper environment, and I would like to get some insight from the cockpit, from the avionics side of things. And our next speaker will be George Papageorgiou, who is involved in many research projects at the Honeywell side of things. So George, how do you see things from the deck, from the flight deck?
So thank you very much, Marwan, and good afternoon, everyone. Good morning, wherever you are. It is a great pleasure to be part of this webinar today. It has also been a great pleasure contributing to the FlyAI report, bringing the industry perspective together with colleagues from Airbus and Thales. So let's kick off with a poll. When do you think that urban air mobility will be fully autonomous? And I'm thinking here, I'm talking AI-powered autonomy. So let's wait a couple more seconds here to get your answers.
Please go ahead, give it a shot.
And here we are. So great to see there's optimists in the audience. I see 2025 at 6%. I also see some pessimists at the 19%. So let's see whether this presentation and this webinar will help to demystify the status of AI applications in aviation and whether you would answer this question a different way by the end of the webinar. So let me go ahead and share here. And hopefully my screen is now coming through. Okay. All right, so AI in aviation has arrived. It is not the future, it is very much the present. Industry is conducting a large variety of AI proof of concepts to understand technical feasibility, deployment challenges, but also customer value. But in some areas, industry is beyond proof of concepts. There are AI-powered offerings for non-certified applications already in service, bringing value to customers. For example, offerings for maintenance applications. So let's take a look at the main areas where AI is being applied with some examples. Vision. So vision for collision avoidance, for navigation, but also for applications like defect detection. There are many applications of vision. The example that you see is an obstacle map that's being created from a single camera, a monocular camera, for the purposes of collision avoidance. Speech, for workload reduction, improved user experience, improved productivity. The example that you see on the screen is a tablet-based air traffic control communication transcription application. If you go top right to time series, for analyzing health and performance of aircraft systems. The example is actually from an APU, auxiliary power unit prognostics application for reduction of aircraft on ground time. Natural language processing, improved user experience and productivity, being able to execute question and answering with a machine, document summarizing by a machine. The bottom two, autonomy and human-machine interaction, actually build on combinations of the four above. Human-machine interaction for simplified aircraft operations. The example that you see is multimodal interaction, where the pilot can use multiple modalities, speech, gestures, touch, for workload reduction, improved user experience, and simplified operations. And on bottom left, we have autonomy, the enabler for new entrants into our airspace, for new operations. The enabler to be able to cope with the predicted growth in amount of air traffic over the next decades. So we're talking drones for last mile delivery, economically viable and competitive urban air mobility, post-COVID-19 growth in commercial air transport. And you may have seen Airbus's A350 autonomous taxi takeoff and landing demonstrations around autonomy. Now, machine learning will power many of these applications, but in addition to machine learning, there will be applications powered by machine reasoning, another branch of AI that enables rule-based intelligent assistance. And there will, of course, be applications that will be hybrid. So a lot of use cases, a lot of POCs, products on the market, but can AI really bring value across the aviation sector? And the answer is, there is no question about that. But in order to realize its full potential, yes, we need to bring AI on board the aircraft, and we need to bring it to the air traffic controller, and that means certifiable AI. Let's take a look at some parts of aviation that AI can bring value to. So I will not just look at the aircraft itself, I'll go through the ecosystem. So in terms of product support, we're talking field engineers, quality engineers. AI and data can improve troubleshooting, can improve technical support and quality checks. Moving to the factory, manufacturing, AI can identify defects and help with productivity improvements within the factory. The images actually that you see are from 3D printing quality checks. Health and performance optimization. This is for maintainers, dispatchers, and pilots. AI can improve prognostic health monitoring and fuel efficiency. Moving now into the cockpit, pilot assist. AI can enable simplified applications, improving safety, reducing workload, improving user experience. And the kind of systems that are being worked on are detect and avoid systems, where you use sensors to detect hazards and avoid them. Pilot state monitoring, so systems that monitor the health of the pilot to improve safety. And multimodal interaction that I mentioned on the previous slide. Last but not least, we have autonomy, the enabler for new airspace users or new airspace operations, the enabler to be able to cope with the growth of the number of operations that we're going to see in the skies. Yes, AI can enable autonomous systems that operate in diverse and complex environments, deal with contingencies, optimize behavior. So definitely AI can deliver value. Let's now take a closer look actually, at an example of AI in the cockpit. There are a number of examples to pick from, but given the short time today, I chose to pick this interesting one here. So Honeywell and Dedalian are working together on vision-based Autoland, integrating Dedalian's AI-powered visual landing system with a Honeywell autopilot. Let me now play a video of a general aviation aircraft flying the Dedalian visual landing system. Here we go. So hopefully it's coming through. The camera that you saw, which is under the wing of the GA aircraft, detects the runway. You can see bottom left-hand side, the runway being detected and the blue box outline being drawn around the runway, and provides flight guidance. So top left, you see the artificial horizon display with a lateral deviation. So runway center line with respect to aircraft. And essentially what you're trying to do, of course, is align those two. And you also see the vertical deviation, the nose of the horizon with respect to the nose of where the aircraft is pointing, if you will. And yes, you're sort of flying a say minus 3-degree glide slope. So vision-based Autoland, apart from being a building block for autonomous aircraft, it can also enable value shorter term. So think of emergency landing in the case of pilot incapacitation. Think of, during bad weather, improved access into airports with limited or no ground infrastructure. So no ILS, not covered by SBAS. Such a system could enable a precision approach. So let me mode here. So we've talked about the value, we've talked about the various applications, but yes, there are some challenges, a variety of challenges that need to be addressed to unlock the full potential of AI. Certification, yeah, we need adapted regulation, acceptable means of compliance to certify onboard systems. To that effect, EASA has released an AI roadmap, and industry is participating in the development of standards through EUROCAE, SAE, AVSI, bilateral projects. We've got data limitation and performance challenge. So to ensure that an AI application meets its intended function, we need accurate data across the whole envelope of operation, including of nominal conditions. We, of course, also need the architectures and the processing power to implement the AI applications. We need trustworthy AI, and that is being able to explain what the system does, ensure that unwanted behaviors are avoided, prevent manipulation of the data used to train the models, enable human control. Those are all critical elements to achieve the public acceptance. Bias and ethics. So in terms of bias built into data is a challenge, and the ethical implications of biased data also. Talent gap. So AI skills are highly marketable. Demand is extremely high across various industries. We have very interesting and cool problems to solve with aviation, but we need to continue attracting the talent. And easy to oversell. AI is conceptually simple and could create unrealistic expectations. We need to be pragmatic in how we deploy AI in the industry and in terms of expectations. Now, to overcome all these challenges, we, the ecosystem, need to continue to work together. The FLY AI report was very clear on that. And the Digital European Sky partnership that Florian mentioned, are ideal platforms for collaborating these collaborative efforts to address these challenges. So, in summary, there are three things that sort of I hope I'd like to get across today. AI in aviation has arrived with many proof of concepts, but also deployed products, applications. 2, AI will provide valuable solutions to aviation, but to realize its full potential, we need to get it on board the aircraft and to the cockpit and to the air traffic controller. And 3, to address the challenges, we need to work together. Thanks for your attention, and back to you, Marwan.
Thank you very much, Josh. Thank you very much for this interesting view from the cockpit, and definitely visual assistant to the crew and all these nice technology is going to help in terms of safety and performance for sure. I remember back in the days when I took flying lessons, and the instructor was saying, we're going to land there in this runway, and I was unable to look at the runway and identify where is it in the cloud, So having this type of devices is going to definitely raise the level of safety and the performance of the whole system. And this is exactly the purpose of this webinar, is really to make you touch a little bit what's going on in the industry in terms of research and innovation, what are the activities that are ongoing, but also what needs to be solved, because we definitely did not solve all the questions, but we have a promising pathway to investigate. The next speaker is actually the counterpart of the airborne automation and airborne activity. So Robin has worked a lot on the ground automation, and Robin, I would like really to hear from you how you see really the progress of AI in the ground systems.
Thank you, Marwan, and thank you for having me today. And good afternoon, good morning, and good night to everyone who has joined us across the world. I would like to start with a poll question, please. And it reads, what were the average number of flights per day in Europe pre-COVID? Was it 55,000, 40,000, 25,000, or 15,000? And whilst you take a moment to think about your answer, ask yourself, what level of automation would you feel comfortable with in ATM? Is there a particular phase of flight where you would feel more comfortable being looked after by an AI? And I believe the answer, right? the correct answer is 25,000. So well done to everyone who got that right. We're not quite there at 40,000 or 55,000, but maybe in 10 or 20 years, eh? Right, so let's go on to the potential of AI. Now listen, there's a lot of great work going on in ATM in relation to AI, and it ranges from improved weather forecasting to improved functionality in the network manager domain to dynamic sectorization. There's examples of AI being used for pre-operations planning, post-ops analytics, everything that we can do to sort of enhance the air traffic management system. And of course, drones are coming strongly equipped with AI for sure. At LFV, we started to sort of ask the question though, how good are you, AI? How much can you do really in terms of air traffic management? And we decided to take a look at the long-term potential of AI and see if we could manage to automate air traffic management in an en route sector, to sort of understand the challenges and the hurdles that we would need to sort of pass to get there. So we launched a project called the Advanced Autoflyer, and the background, or the idea actually comes from Tesla and their autopilot. When a couple of years back they launched the autopilot, and I was actually quite surprised with how quickly society and regulators allowed or were willing to accept, if you like, an autopiloted car driving around in a chaotic environment in our society. So that kind of begged the question, well, if society and regulators are now sort of at a point where they're willing to accept that, then perhaps now is the time to try autonomous air traffic management in a very much controlled environment where we know where the planes are and where they're going. So at LFA, we had a lot of data that we used for research purposes, and we teamed up with the IBM garage in Copenhagen, and through them got in touch with the IBM research team in New York. That was the team that developed the Watson AI that had previously won Jeopardy. So teaming with IBM, we then got active air traffic controllers involved in the project and managed to secure funding from the Swedish Transport Administration, and we were ready to go. Before I get on to the results, I want to talk to you a little bit about the key factors for success. Starting off with full focus on the project goal. We really set out to try and achieve automation of air traffic management. And that, I believe, that always sort of led us towards the results of the project. We created a small modeling team of developers that worked closely with air traffic controllers to understand what the system was meant to do and how it was meant to handle itself. And rather than having doing this based on a sort of typical engineering waterfall methodology, we applied a design thinking process for doing this, and developed a minimum viable product. And that the minimum viable product basically means that we had to create a solution that solved the smallest solution that solved the trickiest problem first, to ensure that we had a good foundation to build on into the future. And for us, that is of course the separation of aircraft, the safe separation of aircraft, which is of course key to the future potential of implementing autonomous air traffic management functionality. And the final point that we felt strongly about at the beginning of the project was that it wasn't really the time to develop a cool neural network, fantastic AI that we then would have to sort of try and understand afterwards what it had done. We wanted to sort of lay the foundation at the core of this function based on a white box AI or a deterministic solution, which can then have increased black box functionality added to it. So these are some photos from an excellent video that's on the LFE website. The link to that video is at the end of these slides. So I can strongly recommend anyone who's interested to go on the LFE website after this webinar, where you can see the auto planner at work. But essentially what has been done is that the algorithm that was developed has then been integrated with a simulator that we have down in Sturup, Malmö, south of Sweden. And basically we allowed it to handle the traffic in an en-route sector of Sweden in a simulated environment. And what the algorithm does basically is that it plays four-dimensional chess. So it forecasts the airspace in the future and finds conflict between aircraft, and then comes up with a set of actions that would solve those conflicts. It then evaluates those actions based on a set of parameters that we have decided how we would like the AI to sort of to guide our aircraft through the skies. And then importantly, for the safety case perspective, it records all the arguments or the reasoning behind how it arrived at the various solutions, and hence arrived at its final solution. And it also records the arguments for why it has disregarded or discarded some solutions, which means that it's comprehensible. It's comprehensible. One can understand how it arrived at the solution that it arrived at. And essentially, we successfully managed to develop this functionality and have a model that successfully separates aircraft and controls them through the sector. There are, of course, future challenges. We have laid the foundation to a potential future with this project. We need to challenge it further by adding more complex traffic. We need to implement various wind conditions to make the space move, just to sort of make the algorithm a little bit more on its toes. An important factor for the future is that we need to consider the time dimension. Today we have a solution that fires as soon as it finds a conflict. We need to be able to plan ahead, maybe 15 or 20 minutes into the future. And why? Well, because we sort of foresee a future where a controller of sorts, a future air traffic controller, an air traffic manager, if you like, will be able to see what the system is about to do. And in order to do that, you need to develop systems and solutions that are comprehensive, understandable, so that you can actually take the role as a monitor and potentially intervene if there is something going on that you don't like. Some learning points that I want to share with you is that get going with your applied AI projects, and prepare to fail quite miserably. We've gone from a data modeling approach to a gamification approach to ending up with a mathematical solution that eventually solved the problem. So start, fail, and restart. I would say to anyone watching and who's curious to learn more about AI, just get going. Here's a link to the video that you can find on the LFE website. And with that, I want to say thank you and hand the floor back to you, Marwan.
Thank you very much, Robin. Thank you. You know, this reminds me of the whole theme of the Perseverance rover landing in Mars, when they said, "Dare mighty things." I think this was the slogan of the Mars lander. Yes, the purpose of research and innovation is really to dare to try new things and to find out whether we can solve our problems in a different way. Definitely the conflict detection and resolution seems to be the holy grail of ATC automation. And it's really a warming feeling to see that there is activity everywhere in the world to solve this issue and make it as safe as possible. Now everybody is curious about what's going on in the military and the secret labs all over the planet. And, so I'm also curious myself to see what's going on in the defense sector. And here we have Ricardo to tell us more about what's going on in your lab.
Okay, thank you, Marwan, for your introduction. It's a pleasure to participate in this session with almost 600 attendees I've seen in the screen. I will just to clarify that today I will be presenting findings of a project we are running for the European Defence Agency, but not myself. I'm not the staff of the EDA. As my colleagues, I also have a poll question to the audience. And here it is. If you were a fighter pilot, would you fly in close formation with an unmanned aircraft powered by artificial intelligence? Here's the question. Let's see the results and how brave is the audience today.
Would you fly?
I would like, but I don't think I'm young enough. As you say, as we say in the FCAS is the new fighter program between France, Spain, and Germany. Here is the results. So most of the people said yes. Okay, thank you. As I was saying, in the FCAS program, we say that the fighter pilot that will fly the new fighter is still in the kindergarten. So I guess none of you in the audience will be in such dilemma.
But the result is amazing. I mean, yes, you have yes from the audience.
Yes, they confide in technology. Yes.
Wow.
I will share my screen. I hope anyone can see the. Okay. Is it working? Is it working? Can you confirm? Yes. Okay. So of course my answer is also yes. And what we will do. I'm sure someone will fly in close formation in the future with a remote carrier powered by AI. And to achieve this challenge, several initiatives have been launched worldwide, as can be seen in the examples I'm displaying. Australia is working with Boeing in the Low-Young Wingman initiative. In Europe, we have the FCAS and the Tempest programs that have the remote carrier concept, is the new UAVs, and in the Tempest, they are called the LANCA, the lightweight, affordable, novel compact aircraft. US, Russia have also research activities. So in summary, there is a lot of work in progress in this direction. And we are facing a new paradigm. We are going from current UAVs to UAVs with much higher performances, close to fighter, and higher levels of autonomy. And why do we need higher levels of autonomy? Well, I would say there is a trend nowadays for automation to autonomy in many domains. I would say everywhere, from automotive, aviation, as we have seen, and we see it every day in home appliances. But there is even a delta in military aviation. If we think UAV is being commanded from a fighter, if we can imagine the workload that the fighter pilot has, we need not to increase the fighter pilot current workload. This is a critical aspect, and it's completely different approach as the current use of UAVs with a ground pilot fully devoted to the unmanned system. In the case of defense, these unmanned systems, these remote carriers, will operate in contested environments, facing enemy threats. So to survive in these scenarios, they need both reactive and deliberative decision making, and deliberative is a challenge. When we're talking about compared to automotive, deliberative is when the car decides that you go overpass the car just in front of you. They need to survive even when the commanding aircraft is lost. We don't want these unmanned systems. Maybe they need to abort the mission if the command aircraft is lost, but we don't want them to be neutralized if the mothership is lost. I remember the film Independence Day, that it's a spoiler, but probably all of you have seen it, that one injected virus in the mothership and all alien fell down. No, we don't want the remote carriers to behave in such way. But at the same time, this high level of autonomy has many challenges. How can we ensure that the human is in or on the loop? We need to have control of the assets. How do we certify this artificial intelligence on board these UAVs? Because they are going to fly over domestic airspace during the mission, for example. And something that has been said this morning in relation with air traffic controllers, but how do we generate confidence and acceptance for the pilot and for their commanders, both, to use this asset in a real operation? In order to tackle these challenges, several initiatives, as research and innovation initiatives, are being running now worldwide. In this slide, I focus in ongoing initiatives in Europe, cooperative programs among several nations, rather than national programs. That for sure there are more national programs and other programs worldwide. At least in Europe, there are two major programs now running. The ones I've already mentioned, FCAS and Tempest, run by France, Germany, Spain, and the Tempest by United Kingdom, Italy, and Sweden. Also, the European Commission, through initiatives like the PADR, this is the Preparatory Action on Defense Research, and the EDIDP, the European Defense Industry Development Program, are launching initiatives also like the ones I mentioned here, also in 2020, where several kinds of unmanned systems were tested in a maritime environment, Drone Edge, or IMUS. IMUS is focusing on UAVs, but also working in this man-and-man teaming, autonomous functions of ground vehicles in this case, but sharing many common aspects. And also, I would like to remark some research activities that are being developed by the European Defence Agency and the European Space Agency. In particular, they are working together in initiatives like Athena, and the EDA has, for example, launched research projects in the use of artificial intelligence in guiding navigation and control for aircraft, or one related to the safe autonomous flight termination of safe term. That is the one that I will present in this slide. So the idea is to show you that these activities are ongoing, and some results are being found. In particular, safe term we are running together with our partner Artec for IDA. The project started in September 2019, and in this project we are focusing in one specific aspect of autonomous operations of UAVs, US, to ensure safe flight termination in case of emergency. As I said here, we want the UAV to emulate Captain Shelley. It's would be the target of this type of project. I would like to remark that for me, this is a clear example of research and development in defense that is fully applicable to the civil domain. But I would say that the concerns of the risk associated with the operation of UAVs are maybe more on the defense side, because they operate the bigger, currently what they call the male and the heavy. So the biggest UAVs being operated nowadays are being for government use in defense and security, for including flights over domestic airspace for maritime surveillance, search and rescue, firefighting, forest firefighting, etc. So one point regarding safe turn that I think is relevant to mention is that we are working on technology, and in parallel we are assessing the onboarding of these technologies in UAVs from two perspectives. First, we consider that on board we have limited computational resources. So I think that has also been addressed by my colleagues that we don't have the cloud that Amazon has when we are trying to run AI applications on board a UAV. And the second aspect is taking in consideration the certificability of such technologies. In the SESAR project, we are using the term predictability of the UAV behavior. So how can we combine AI, machine learning, maybe with rule-based, so we can have some kind of, not, I would say, not deterministic, but at least predictable behavior of the AI. Just going a bit further in the project, well, what we are working is in a state-of-the-art AI and machine learning techniques for vision processing, machine vision, whether you like to refer to it. The idea is that the UAV takes off with a predefined list of alternative flight termination areas, AFTAs. And in case of emergency, and assuming one of the cases, one of the situations can be we completely lost control with the ground pilot, so the ground pilot has no means to send commands to the UAV, so the UAV has to operate autonomously. The SafeTurn system on board launches two processes in case of emergency. First, we activate the calculation to check if one of these pre-planned areas of landing can be reached. And in parallel, we start the visual scanning of the ground to look for improvised AFTAs that meet the requirements that we impose to the system in order to minimize the threats to population. We are looking for water areas, we are looking for unpopulated flat grounds. So the idea is to try to land as secure the UAV, and at least at a large scale will be to destroy it secure, not if we are not able to perform a landing. We have achieved initial results of the project. We are working in a proof of concept initially using extensive use of simulation, validation by simulation, and it's not it's not planned to have real flights in the scope of this project. It's just a small or mid-sized project. Just to have a few last slide, sorry, about the challenges. I think that the challenges are common. Most of them are common to the ones that have been told by my colleagues. And most of them are common to every application making use of AI machine learning in aviation. The certification roadmap, achieving trustworthiness, explainability, robustness. How can we be sure that this will behave as it was designed? There are other aspects, the one regarding deployment, more aspects applicable to UAVs, as I said, where we have limited computational resources on board. And regarding training, I would like to raise an additional point. It's always difficult to get enough data sets for training algorithms, but I would say it's even more challenging in defense domain. Even more challenging in defense domain, the lack of data sets is a problem. We cannot generate data sets cooperative in the same way that other applications do. You cannot reuse, or you cannot do transfer learning because you may have hidden data or hidden problems in that data sets. So it's more challenging in the defense domain, and we have to make intensive use of high fidelity models and simulators. And that was my presentation. Thank you for your attention, and I pass the control back to Marwan.
Thank you, Ricardo. It's fascinating how we did not really coordinate the slides all together, and it's fascinating to see the same challenges appearing in all fields, military, civilian. We all would like to take advantage of this technology, but also we have to make sure that it's safe, explainable, training. By the way, some of the aspects that you guys mentioned are going to be tackled by other webinars, such as training. I think the last webinar series will be about training. So if you're interested in that, make sure that you follow the webinar series. Now, our last but not least speaker is Dr. Hartmut Emke. He will give us a bit more insight into the applied research and fundamental research in the area of machine learning and especially speech recognition. Hi, Hartmut.
Thank you for the introduction. Yeah, good afternoon, good morning, good night, as everybody has said. I have also a poll question. Maybe you can show that. Yeah, it's about a company many of you maybe know, but not all. I heard this company is coming from the English word to Google. Yeah, how many data you think? I see the number of people is decreasing and decreasing here during I'm talking, but yeah, I have the biggest number on my slide, so in my poll question. Okay, so I will start my talk with an introduction of, okay, thanks for the answers. I will go on the last slide again to this poll question. In the beginning, I want to start my presentation with just going into the details and the definition. Yeah, what is artificial intelligence? Yeah, I took you a newer one. Well, artificial intelligence is the development of computer systems that show human intelligence. Yeah, if we take that definition, maybe 80 years ago, well, multiplying numbers would be then already intelligent. Or doing my studies in the 80s and 90s, playing Go or chess playing, that we would define what a computer will never be able. Yeah, that's intelligent. Or yeah, currently in the current talks, yeah, autonomous cars or zero-person cockpits, that might be intelligent system. Though the definition really depends on when you are asking this question. Well, another try to define artificial intelligence was maybe during the 50s, already from Alan Turing, the so-called Turing test, which he said, well, put a human next to a human and a machine, and the human asks questions to the machine and to the human, and if he's not able to decide who is answering, well, then we define this system an intelligent system. Well, other approaches, well, to address what is artificial intelligence, well, look onto the applications currently, and well, currently everybody is talking about machine learning is already the only thing that makes artificial intelligence. I think that's not true, and also not talking about only neural networks are at the moment machine learning. Yeah, there are much more techniques. So yeah, artificial intelligence, as my speakers before already said, is natural language processing, computer vision, robotics, expert system planning, or in my area, more applications of automatic speech recognition. Well, when I was preparing this talk, somebody asked me why expert system has failed during the 90s. Well, and when about thinking about, I would say, no, they have not failed. Nobody is maybe talking anymore about expert systems at the moment. They are just applied. They are in the systems, decision support systems. If you are getting or you're going to the bank, or well, the algorithms make many of the decisions and support you. Though expert systems are not a failure, and I expect that also 20 years further. Most of the techniques we are talking about now are then in operation. We are not calling them any more artificial intelligence. Yeah, now a little bit more to my area where I'm coming from, application of automatic speech recognition. That means, well, I have a controller talking to the pilot and a voice-to-text system, though the controller is saying something like, good morning, Turkish 5 Kilo Juliet, reduce 160 or greater, descend 3,000 feet. Yeah, and you need to understand these words, word by word, but you need really to understand that. So you need to extract where is the call sign, what command is given, what are the values. Yeah, and that we are doing at DLR 7 years ago. We invented assistant-based speech recognition together with Saarland University. And well, that means we try to use an assistant system which predicts what the air traffic controller might say in the current situation. And well, that really helps to reduce the search space of the speech recognizer. For this purpose, we are using surveillance data, flight plan information, weather data, though just context. Well, some people say, well, that's not application of artificial intelligence anymore. That's not pure speech recognition. Yeah, maybe they are right, but it solves the problem. And well, at the end, of course, you have to show what you have recognized here, that you have some value for the controller. Maybe you show it in his electronic flight strips in the radar label. That we have applied for Düsseldorf approach area 7 years ago. I think it was a successful application, but we needed to invest a lot of money for that. A lot of human experts were needed, and if we want to bring that into operation for different approach areas, well, we thought it was too costly. Therefore, we started the so-called Mallorca project. It's not the island, it's only with one L, though it stands for Machine Learning of Speech Recognition Models for Controller Assistance. And in that, well, we thought that let's use all the radar data and the speech data from an airport, which we can get, so from Prague and Vienna approach area, for example, and then automatically learn the models for these airports to have an assistant-based speech recognition system for these. So what we did, as I said already before, we just replaced human expertise by machine learning to make it cheaper. So looking on the roadmap of speech recognition and machine learning during the last 10 to 7 years in Europe, we started with the Eglisten project, in which we could show that assistant-based speech recognition is possible, and we can on command level achieve already a recognition rate of 95%. We continued and we quantified the benefits for the controller, where we could show, well, that we reduce the workload with speech recognition, and we could reduce fuel consumption by using speech recognition by 60 liters of kerosene per flight. Well, in the Mallorca project, we're more focused on the error rates, not on the recognition rates, on the error rates, and here we could achieve for Prague on command level 0.6 and for Vienna 3%. And well, as researcher, we were involved in this wave 1 of SESAR projects, where with other partners we used commercial off-the-shelf speech recognizers to bring them closer to the ops room, which we are continuing now in wave 2 in various projects. And well, the interesting part, the SESAR project, where we are now involved with 7 partners, of course, from Mallorca you come to Hawaii, and in the Hawaii projects we are really addressing the problem of, well, we want to recognize pilots, we want to do readback error detection, and well, we're also addressing one of the most complex areas which you have in Europe, the London GMA. So that's what we want to do during the next 2 years with speech recognition. And coming to my poll question, can you see something? Well, you should see this here. This small dot means, well, in the Mallorca project, we have used 22 hours of voice recordings from Prague, just for our learning purposes, okay, together with some other data. But if you're looking at what is Google using currently, it's really 300,000 hours. And maybe the guys who pointed on 3 million are even more right, because I think that are the numbers 3 years ago, and everybody has used already his voice data to support Google. Thanks for that. Thank you again for that. So but in Europe we also have achieved a lot. And well, let's use it now. And well, 22 hours is not much. Well, we need to join here our forces, or many people many ANSPs are involved in speech recognition and data. Data is needed. And well, of course, the step from research to industry could be faster, which puts requirements, well, on both, on research side, but also on industry. And well, I mean, artificial intelligence is just a technique which can generate benefits. So let us not wait until we have a perfect system. Of course, there must be a good risk management, but let's start it. Artificial intelligence, however, is more than machine learning, but you should not ignore the benefits and the possibilities of machine learning. Though I think due to the time, I always said you can talk about everything, but not more than an hour. So I'm stopped now, and thanks for your attention. I'm looking forward to the questions of the discussion. Thank you very much.
Thank you very much, Shahmoud. Thank you very much. I remember when I first was introduced to you when I went to Braunschweig there, and I was with Helmut, and you start pitching this idea of Hawaii project, and I was saying, look, I have my phone here. I mean, this recognized my voice and everything. He told me, really? Okay. Tell him, Lufthansa 134, turn right, heading 180, and speed this and much. And then I saw the result, and it was nothing to do with what I told the algorithm. So this is definitely, aviation. I mean, the algorithm is trained for let's say the normal conversations. It's not trained for aeronautical language, and it's important that we have the proper data, the proper framework to train and develop. Thank you for everybody that stayed up till now for this webinar, because this is the exciting part of the webinar. This is the part where you got to ask the questions to the panelists. Thank you guys for all the presentations. I think it was quite an exercise to condense all this material in this short amount of time, but hopefully we left a bit of room for the Q&A. Just some message for people who ask questions. This webinar is about research and innovation in AI for aviation. So forgive me if I don't address questions that are a bit outside the scope of this webinar. The first question, let's say the first popular question is, can you please elaborate on the risk of the AI learning the wrong suboptimal controller behavior, controller action as they are now, but not how they are supposed to be? It's a very interesting one. I see you, Samir, smiling, so I would address this question to you.
Yeah, of course, there is a need to debias the data. And machine learning techniques allow us to identify the noise or the outliers which can be identified. There is a need to establish an envelope or a set of boundaries which we see in the data. So I believe these are the techniques of debiasing the data and learning a normal behavior from the data might be useful here. So as more data will be required for training from the controller action, we believe that those outliers or those noises can be suppressed. In less amount of data, certainly there is a challenge, but as more data is available, the law of averages will kick in and we will be able to see normalized behavior.
Thank you, Samir. I think it's a very interesting one because I heard discussions about, should we teach the algorithm how the human behaves, or should we leave the algorithm to generate solutions on the basis of the rules of separation? And it's actually touching upon interesting topics such as the trustworthiness and the machine generating quite weird patterns that are not necessarily understood by a human being. So next question is about eVTOL. Will AI allow new eVTOL aircraft to operate autonomously in controlled airspace, especially in urban areas? So I will perhaps address this to Georges. Georges, what do you think? Will AI allow for new eVTOL operations in controlled airspace?
So I guess there's a stepped approach to get there. So there are certain challenges, right, to get to autonomous aircraft operations. There are so Samir talked about sort of data-related challenges. I'll mention another one, like interpretability. So being able to understand how we got to the answer, being able to trust, if you will, and have confidence that the digital pilot is making the right decisions using factors that work not just 95% of the time, but 99.999% of the time, if that's what the intended function requires. We need public acceptance, right? So the public needs to accept these autonomous vehicles. Yes, there's a lot of activity going on in other industries, like the car industry, with semi-autonomous vehicles that promise to save lives. So by seeing sort of autonomy all around us, that will also help. And then there's the HMI perspective, right? So as we go to autonomous vehicles, the pilot does not disappear from step one, and we need sort of HMIs to evolve. So Maran, I guess, yeah, can AI enable autonomous eVTOL operations? I think, yes, there is promise for that. We can get there. But in order to get there, we're going to have to basically address certain challenges. And we're not going to get there in one step. There is going to be a stepped approach where, and you can see also all the eVTOLs, I mean, they're all starting with a pilot in the loop. We're going to get those off the ground. Then we're going to go to simplified operations with new HMIs, where so the machine is doing more. And eventually, yes, we will get to potentially autonomous operations. And if you will, from a business standpoint, I mean, we need to be able to get there to have economically viable and sort of competitive urban air mobility.
Thank you, George. It's an interesting question for sure. Now, there is a bit of a worry here. They say, in this new virtualized, interconnected, highly automated environment, we are entering ATM, air navigation services. What are the boundaries, the limit should we put on AI so that we can maintain control? I think this is the point of making sure that the machine does what it's supposed to do and does not exceed the boundaries. I don't know who wants, raise your hand if you want to take this question.
Well, I can try that. Or
okay, Professor.
Yeah. Well, I think it depends on the application. Or if you just are using artificial intelligence, don't mix that with autonomous system. If you are using artificial intelligence, or for example, for speech recognition, it's just a support tool. The human still has to decide. And well, if understanding of the machine is better than the human, well, why not using it? So my answer would be artificial intelligence is just a technique. It has still nothing to do with autonomous systems. If you're talking about autonomous systems, it's another question.
Okay, and what about the fact of putting boundaries to the output of AI so that it does not exceed any kind of safety margins or stuff like that? Is this something that we can hard code in the system?
Well, that's one of the approaches, yeah, to control this, but only one, and I think that always depends on the application which you have. So if you use it for speech recognition and you recognize descent to flight level 2 million, yeah, maybe that's the easy thing. That's the easy thing. But yeah, descent to flight level 100, is it true or not? So it depends on what is then the effect of your other aircraft near it, or so.
Exactly.
But it's easy. You have the controller for that application.
And by the way, the audience, if you have questions that are not answered, please go ahead and contact the speaker direct. He would. I think the group is really eager to take on board some of the questions directly. Another question is about. Really, the learning process. Okay, we understood that from an ATM perspective, the config detection or resolution is an important bit, and that the algorithm is fed by data. Sometimes you don't have that much data, and there is a need for standardized information. So, how can we make sure that we can enrich this ecosystem of data? Maybe Robin, did you face any data issue for your experiments?
Can you just clarify what is the question, Maran?
The question is the need for standardized approach. Let's say you fix a problem in Malmö, but it's still valid for Stockholm, or you fix a problem for Sweden and still, you have to work it out for another country.
Well, let me comment on that in this way. When we set up the Autoplanner project, Autoplanner is actually a really bad name for it, because it's not a planner anymore. That was the initial intent, to sort of address it from a planner perspective. But we soon sort of found out or realized that the relationship between a planner and an executive air traffic controller varies slightly. There's a human to human nuance in how they interact and so forth. So we actually decided to take a new grip on air traffic control for that very reason. I'm sort of answering another question I can see on my big other screen here, but and so I think if one addresses the question of artificially enhanced air traffic management, one can do that from a general perspective. There are always going to be rules and nuances to the variations in airspace and type of airspace. But if you solve the fundamental problem, ensuring safe separation and guidance and so forth, then my opinion is that it should be okay.
Okay. Samir or anybody, do you want to jump in for the need for standardized material?
Actually, the fundamental difference between the machine learning approach and the classical symbolic AI approach is the move away from having a general purpose machine that can do everything. Machine learning algorithms are very specific for a very specific problem, trained on a specific data, trained on a very specific sector. And that's what actually has changed the acceptance of machine learning. When the algorithm was developed to just recognize digit from 0, 1 to 9 for the United Postal Services, they give very good results rather than having a machine learning that can recognize everything written. So instead of having a standardized set, I think the more focus should be on a specific problems, looking at a specific data set and training for that. Mm-hmm. Machine learning, which can do a general purpose thing, will be very challenging. That's why my focus is always on a personalized tools for air traffic controllers, which are trained by themselves, and their activities or resolutions in this case are very similar to the way controllers by themselves have acted on such scenarios.
Okay. Thank you, Samir, for complementing this. Now I'll come back to our first speaker, Florian. You see that there are a lot of innovations ongoing, some of which is really supported by SESAR, some of which supported by the industry or research labs. How can the tissue of research stakeholders and ecosystem fast track this type of innovations in the future?
Well, I think this is one of the ideas that we have with the setup of the future SESAR program to create the right platform so that we can work together on such topics. I mean, looking at the list of questions, I've seen many genuine questions and concerns about the use of AI in our domain and the impact it could have in terms of safety. I think one of the elements that we need to move forward in the way we progress towards implementing AI solutions in air traffic management is actually to enhance safety. I do believe that from the examples that have been mentioned already, we can see that there is a potential there to improve the way we deal with the traffic currently, to improve the solutions that we provide to the pilot and the controllers, and that actually we can demonstrate that there is a safety benefit. And so to me, this is an area where we can have somehow a common understanding that we use AI for the benefit of safety in aviation. And then there are probably a lot of other applications that could be useful at a later stage, but maybe let's start with that, because I really believe that when we see, for instance, the potential of enhanced vision on the airports that has been just shown earlier on, we do see immediately that this can bring additional benefit in all sorts of weather conditions, for instance, and the number of assistants that we do not have today that can definitely improve the way we provide safety on an airfield. The other element is that we have to team up as well to work on data. And I do believe this is a substantial effort that has to be brought into the work that we do. The accessibility of data, the way we can support the work of the scientists, of the researchers, of the industry in that domain is one of the challenges that we foresee in the future SESAR program. That's why as well it's very important that we have Eurocontrol as a founding member of the future activities to bring as well the network data that can be used to perform those research activities. I was just making a very simple calculation on the basis of what Hartmut was saying in terms of a number of recorded hours that could train Zen systems. And he was mentioning those, I think, 22 hours that have been used. If we look at the amount of traffic we had in Europe in 2019, multiplied by an average of 2-3 hours of flight for each and every flight, it reaches very quickly something like 30 million of hours of recording. And we have those recordings because they are necessary for safety purposes. So let's try to start to tap into that and to use this for the purpose of the research first. And then once we demonstrate through research that we have additional safety benefits, that we move that into the operational environment.
That's a very interesting insight. We are sitting on a mountain of data and we're not using it perhaps the right way. And we should dare mighty things, right? So let's dare to use this data to solve and perhaps create a bigger pot for the tree, Florian. Okay, guys, I'm sorry, I cannot go through all the questions. We're getting to the end of our webinar. I would like really to thank the speakers and the panelists for your time today. It's really fantastic. I know we cannot go through everything in details, but I hope this webinar helped you a bit to fly around and to get a flavor of what's going on in the research and innovation in AI for aviation. Stay connected with the speakers, stay connected with SESAR, with Eurocontrol, with the high-level expert group. There will be a series of webinars, as I mentioned at the beginning. The next one is about ATM enablers and use cases. So I'm sure you will have much more material for the next webinar. In the meantime, I would like to thank you for staying until the end of this webinar and looking forward to seeing you in the next events. Bye-bye.
Bye-bye. Thanks to the host.
Bye-bye. Thank you very much.
Bye. Thank you.
Thank you all. Thank you so much. Well done.
Thank you. So then now really good night to Singapore.
Thank you, Atmut. Thank you. Bye.
Bye-bye.